So hi everyone. First of all, I would like to thank the organizer for giving me this opportunity. And I couldn't come attend the conference in person because of some health issue. But I would like to discuss my work. So today I'll talk about inverse soft construction of scattering amplitudes. And this work is partly based on the paper which came out in 2023 and some ongoing work. And it's done in collaboration with Sudarshan Anand, Nipun Bhave, and Chetan Pandey. So okay. First, before jumping into the work, I'll give a brief motivation. Although the conference is about scattering amplitude, so I don't have to motivate why scattering amplitudes are interesting. But a brief motivation related to my work. So, scattering amplitudes are objects of interest in quantum field theory. Off-shell Lagrangians introduces redundancy, and traditional methods are not very efficient in amplitude computation, which I think we already have seen in some of the talks. And the discovery of spin and LCD variables have led to simple on-shell recursion relations. And some two prominent methods are BCFW recursion relation and BCG relations. So in this talk, I'll briefly outline one such method, which is inspiration from BCFW recursion relation. And here the idea is this that can be recursively construct scattering amplitudes using the inputs from soft theorem. So I'll first delve into what are soft theorems. So the idea is very simple. So consider a n plus one particle amplitude. So the n legs are denoted by p1 to pn, and the n plus one leg is denoted by n momentum k. So in this case, I'm talking about soft theorems for boson. One can similarly do for fermions and scalars. So the Weinberg's theorem simply states that if the one of the external momentum k goes to zero, the amplitude at leading order factorizes into a universal soft factor times a lower point amplitude and plus some subleading and sub-subleading correction. And this was first in the context of gravity was given by Weinberg using Feynman diagrams. In the context of photons, I think this was given by F.E. Low. And by universal, what I mean here is that the soft factor the soft leg actually does not depend on what hard leg it is attached to it. It can be of any spin, whether spin 1, spin 0, spin half, so it doesn't depend on anything. So it's universal in that sense. And in the last 1 decade, there has been great renewed interest and a lot of progress in the study of soft theorems, particularly in the context of asymptotic symmetries and celestial conformal field theory. So my main motivation would be is to can I use this soft theorem idea to recursively construct scattering amplitude? And the question and the answer to this question is partially yes. And this idea is very old. The idea came up first in 2010 and then in the context of Grassmannian and then was done in the context of gravity and gauge theory. And I'll talk about this idea in the context of higher dimensional operator. But let's see what is the idea first. So the idea is this that higher point T level amplitudes can be constructed from the shifted lower point ones by multiplying a universal soft factor. The important thing is shifted lower point amplitudes. So I'll first discuss this in the context of gauge theory, and I'll talk about a class of amplitude in the context of gauge theory, which are MHV amplitudes. And the idea is very simple. Take the universal soft factor, multiply with the lower point amplitude, and this lower point amplitude is the shifted one, and the some of the legs in this lower point amplitudes are shifted. In the case of gauge theory, only two adjacent legs are shifted because in the case of gauge theory, we know we can simply strip off the color factor and just work with the kinematics part. Okay. And this shift actually depends on two factors. First, it depends that the fact that on the left hand side, we have one extra leg as compared to the right hand side. So we have to keep the momentum conserved on the both side. Also, it depends simply on the helicity of what soft leg you're attaching to the lower point amplitude. Okay. And this inverse soft construction is only valid for the amplitudes which are constructible in the usual sense of BCFW. So this can be trivially actually applied for gauge theories and gravity because they have been proven to be constructible using BCFW. And this was first studied, by Larkowski and Dhritima Nandan in the context of gauge theory and gravity. So I'll first give the example of Yang-Mills amplitude, which has been already done, and then simply will build this up in the context of high dimensional operator. So let's first look into the soft factor for soft gluon. And as I just told you that the soft factor, the soft leg can actually depend on any of the hard legs. So if I have n plus one amplitude, it can be attached to any of the nth legs. But in the context of gauge theory, we have color order amplitude and the soft leg can be only attached to two adjacent legs, and uh, therefore this I, instead of running from 1 to n, actually just depends on the two adjacent legs. Also, if you notice this R is this reference momentum leg, and when we simply sum over these two adjacent legs, the soft factors actually comes out to be independent of the reference momentum we are working, and this is an artifact of gauge invariance. And a similar thing we will see simply will be true in the case of gravity. And this gauge invariance of soft factor can be used to rule out why higher spin theories don't exist in nature in the context of flat space, and I'll simply comment about it at the end. But let's first see how we can simply use this idea of inverse soft to construct higher point tree level gauge theory amplitudes. So I'll first just focus on the MHV class amplitudes. By MHV amplitudes in the case of gauge theory, I mean simply that there are two negative helicity and rest all can be positive. So the idea is very simple. Let's take 4-point amplitude. And to construct 4-point amplitude, we take the seed amplitude, which is 3 point, which can be just trivially constructed using Poincare invariance. And the idea of inverse soft is this: take the seed amplitude, lower point amplitude, shift the adjacent leg, and multiply with the universal soft factor. We use the following shifts here. And again, as I just told you in the last slide, the shift actually depends on the helicity of the soft leg which I'm attaching to my lower point amplitude. And the second fact is that I have to simply keep the momentum conservation on the both sides. And for the case of gauge theory, the simple fact is that the MHV amplitudes are purely functions of angle brackets, and anti-MHV amplitudes are purely functions of square brackets. So the inverse soft construction is actually very trivial. So I don't have to shift any leg here because of the shifts that I'm working with. So to construct MHV amplitude for gauge theories, all I have to do is take the low point amplitude and multiply with the universal soft factor. And in this way, we can construct MHV amplitude. As we go for NMHV amplitudes and higher NMHV amplitude, this construction simply fails for certain class of amplitudes and is only true in certain classes. Okay, now in the case of gravity, things are slightly more complicated because in gravity, there is no color ordering. Since all legs are identical and we have this permutation symmetry. So this soft leg, which I'm attaching to my lower point amplitude, can be actually attached to any of the legs. So now, because of that, the form of the soft factor is complicated. And also the important thing here is this, that the MHV graviton amplitudes are no more functions of only angle and square bracket. Beyond 3 point, they're actually functions of both angle and square bracket. So the inverse soft construction is slightly more involved, and we actually have to employ the shifts to simply construct the higher point amplitudes. And in the context of graviton amplitudes, this inverse soft construction actually fails beyond the 7 points. And this was first shown by Andrew Darkowski and the author in 2011. So our motivation was to basically take this method and employ in the context of high dimensional operator. And what we wanted to understand was this, that high dimensional operators are usually not constructible, and also using the standard methods, they are shown that, okay, either one has to employ all line shift, or either one has to simply shift more than 3 or 4 legs to simply construct even the simplest amplitudes. So the idea was this, that can we use inverse soft method, keeping in some usual rules in mind, that can we construct some higher point amplitudes, the answers to which are already known. So what we do is we only consider amplitudes here with single insertion of higher dimensional operators. So in the case of, suppose I want to construct amplitude with f square and f cube. So one vertex will be from f cube and the other will be simply from f square. And similarly, for in the context of r cube, the same thing will happen. So what we do is we take the simplest example, f cube, and usually covariantly the way to get the 3-point amplitude is insert the self-dual and anti-self-dual field and simply see that the f cube operator decomposes naturally into holomorphic and anti-holomorphic part. Since we're working in the light cone gauge in the first part of the paper, and light cone gauge involves the physical degrees of freedom, this f cube operator naturally decomposes into holomorphic and anti-holomorphic part. So this is the 3-point amplitude, and this is the anti-holomorphic part of it. And what we notice here is this, that as compared to Yang-Mills in gravity, here the full amplitude is actually the function of holomorphic part and anti-holomorphic part. Also, since we have added one more operator in my usual Yang-Mills theory, the soft factor has has to change. But what really happens is this, that the leading soft factor for Yang-Mills and also for gravity does not change. And this was first shown by Elwang and company in 2017. So we don't have to do anything. All we have to do is we have to simply take the lower point amplitudes from this theory and use the usual universal soft factor for Yang-Mills or gravity and construct the higher point amplitudes. So the construction actually follows through the same way. And at 4 point, only the holomorphic part will contribute, and the answer trivially comes out to be simple. It's the multiplication of the 3 point amplitude, which can be just obtained using Poincare invariance and the universal soft factor associated with the Yang-Mills part. And the one non-trivial part is compared to Yang-Mills, it comes here, is that beyond 5 point, what really happens is this, that both holomorphic and anti-holomorphic part starts coming into picture. And one cannot actually construct the full F-cube amplitude beyond 6 point using this inverse soft method, because higher point amplitudes are not constructibles in the usual sense of BCFW here. So what one can do is one can just focus on the holomorphic part and construct all the higher point amplitudes here. And the idea would be very simple. All one has to do is take the universal soft factor and multiply with the lower point amplitude, keeping in mind again the appropriate shifts. But since this is purely holomorphic, the shifts won't play any role here. One can similarly do the same thing in the context of gravity also. And what comes out is this, that the holomorphic part of the graviton, this R-cube operator's amplitude is actually proportional to the graviton amplitude up to some factors. And we did the same thing for this HF square operators. And what we did was we also tried to construct some NMHV and N square MHV amplitudes for 5 and 6 and 7 point amplitude here to see how much we can push this method. Okay. So now coming to the summary and conclusion. So what we found out is that this inverse soft method is actually an alternate tool to construct amplitudes recursively. And particularly for a class of amplitudes like MHV amplitudes, this is a very simple method because we don't have to do we don't have to talk about what are the shifts that we have to work with, because the amplitudes are purely functions of angles in square brackets, and one can easily construct MHV part of the amplitude. The other interesting part that we found out was this, that higher spin theories, which has been shown that they are not consistent using different methods, can also be shown using this method that they are not constructible, or the higher spin amplitude does not exist, or higher spin theories does not exist in flat space. And some open questions and interesting part that I'm still thinking about is, the first thing which is very interesting is this, that how can we construct the non-constructible amplitude using inputs from soft theorem and some additional symmetries. And this is along the similar work which I think Cliff Chung and Yara Trnka did in 2015 and 2016 for effective scalar effective field theories, where they added some additional symmetries and was able to construct the non-constructible part of the amplitude. The next interesting thing would be here is to simply see, can we construct the Park-Taylor-like formula for full F-cube and R-cube operator, not just for the holomorphic and anti-holomorphic part. And I believe for that, basically, we need to simply answer the first question here. And the third and the most interesting question would be, can we have a similar Hodges-like formula for MHV amplitude with insertion of higher dimensional operator? Yeah, with this, I would like to conclude. Thank you.
Thank you, Saurabh. Any questions for Saurabh? Okay, maybe I'll ask a question. So is this the same as just doing BCFW for MHV amplitudes and looking at the term that you get out, which is one term?
Yes. So, I mean, the expression that I showed, I mean, this formula actually is actually derived using BCFW as an input. But once you have, once you know simply how to construct any endpoint amplitude using inverse soft, you don't have to think about BCFW, or you don't have to simply think about the shift, or have to think about what is the Z that in the shift is there. All you have to simply take is the soft factor and the lower point amplitudes, with keeping in mind what are the shifts. So, and these shifts are actually independent are different from the usual BCFW shift that we have. So, but the basic recipe is BCFW only.
Yeah, just a small question, Saurabh. So how do we know that these shifts are valid in general? I mean, has anyone looked at the large Z behavior of these shifts for generic helicity configurations of the external particles? Or
so, as I just said, I mean, the way to simply obtain, suppose this expression is actually start with the BCFW sub diagrams or sub amplitudes for graviton, and simply obtain this expression. So first you have to simply draw the sub amplitudes there and see what are the shifts, and you will simply find out that the usual BCFW shifts that you have, and where the large dipole is absent, only for those classes you can only have inverse of. So suppose pi4 theory that you know simply is not usual BCFW constructible in the usual simple theories, you will simply see the inverse of construction also won't work there. But if you take a supersymmetric theory, you know the phi4 theory is constructible using the super BCFW shift. The same thing will happen here also.
Okay, thank you.
Yeah.
Okay, let's thank Saurabh again.